In my study of Chinese characters, I find it useful to use flashcards to memorize the characters. I have a program created by Nodtronics which shows one side of the card with the English definition and the other side with the corresponding Chinese characters and a spoken example. The program allows for answering by flipping both ways, because it is not necessarily as easy to remember the translation from one language to the other as the reverse may be. It allows for both computer-assisted checking of the answers and for self-marking, which is good if you can accurately describe your knowledge of particular cards. The program allows entering Chinese characters using a pinyin input method. Pinyin is a phonetic representation of the sounds of the Chinese language written using English characters and tone specifications. Whilst this method is good for practicing pinyin, it does not allow me to practice the strokes required to write the Chinese character. Seeing a Chinese character and recognizing it does not necessarily enable me to draw the character from memory. Consequently, I wanted flashcards that would allow me to draw the characters. I selected a list of words for memorization based on characters that I already knew with unknown characters attached to them, and typed these characters into Microsoft Paint along with the pinyin and the meanings. I allowed space to write the characters after covering them. This is the equivalent of look, cover, write and check. I used a tablet input device, which is an excellent writing tool. In the end, I was recalling the whole list from memory in the order in which it was written. This is not necessarily conducive to random recall of the information, as the first item on the list is then remembered and each subsequent one based on the alphabetical order of the pinyin. I needed a random presentation of the cards, so I decided to program a JavaScript hypertext markup language document that would perform in a similar manner to the Nodtronics program. The 3 items per card that it could display would be the characters, the pinyin, or the meaning of the card. The Chinese characters were encoded as Unicode within the JavaScript program using an ampersand and hash characters, decimal numbers, and the semicolon character. I was able to convert characters from pinyin, which I entered, into a program that I found on the internet. Each of the cards was stored in array variables containing the 3 possible items, and a random number would select the appropriate card. Another random number would select one of the items to be displayed in black on the web page, whereas the other 2 items would be displayed as white, hence invisible. 2 buttons were also present at the bottom of the web page, which allowed the extra items to be displayed as black, or for a refresh of the web page and random card to once again be selected. For optimal learning, it seems there should be a certain number of cards in this list, so that the amount of time between seeing the same card again is low enough for it to be on the threshold of your short-term memory capacity. I usually had the amount of cards set at 20, with many different sets of cards and large conglomerations of up to 128 cards that I thought would give me a good idea of how many cards I would forget when not seen in the context of the small lists of cards. Creating these lists is a task that requires quite a bit of effort, and going through the same sets of cards when you might be trying to remember 1 or 2 of the cards, whilst the others are firmly placed in your mind, can be annoying. It would be useful to include information about each of the cards, which could be accessed by the program to determine how likely those cards were to be shown again. It is very difficult to store information as retrievable using JavaScript because there are security problems. There is a Creative Commons Chinese-English dictionary that I used frequently in my studies that consists of a Unicode file with the characters, the pinyin, and the meaning of the word. I intend to use this for my flashcards program. When I looked at this file, I saw that it had a Unix timestamp number. Intrigued by this number, I found that it is an encoding of time that represents the number of seconds since midnight on the 1st of January 1970. Any time since then can be described by this number, and depending on the precision of the number that is used to represent it, negative numbers before the year 1970 and positive numbers after the year 2038. I think that this representation of time will be useful for my flashcards program, because it could give an indication of the last time a particular card has been viewed and the likelihood that it has faded from memory. The first step in making my new flashcard program would then be to devise a way of converting the current time into a Unix timestamp. The reverse method is not so critical, because once the timestamp is achieved, that number can be used to compare with other future timestamps. The format of the date will record the year, the month, the day, hours, minutes and seconds, and these must be converted into the number of seconds after the start of the first second of the year 1970. The process would be simple if it weren't for leap days. If leap days occurred every 4 years, it would be relatively simple. Still, but an added level of difficulty occurs because there is no leap year in the years 2100, 2200 and 2300. Because I have faith that my program will last this long, I need to make provisions for this occurrence. The first step in my solution was to realize that the Gregorian calendar repeats every 146,097 days, as explained in an Internet Wikipedia article. This provides me with the information needed to specify when each of the 97 leap days occurs, and to create an algorithm that detects that a certain number of leap days have already occurred when a day is specified. Between certain numbers of Gregorian days, there are a fixed number of previous leap days, so these can be specified by if statements. The first leap day occurs on the day 789, counting the 1st of the 1st 1970 as day 0, and every 1,461 days afterwards until day 47,540. A mathematical statement can be formulated to give the number of leap days until this period. Other sets of leap years within the cycle are calculated in similar ways. I used the 32-bit integer primitive types to describe these calculations, and consequently any fractional remainder in a division is discarded to leave only cardinal numbers. If floating point numbers were used, then a function known as floor in the math library would need to be used. The leftovers from divisions are however used to calculate hours, minutes and seconds from the timestamp by subtracting the result multiplied by the initial divisor from the initial amount. These numbers are easily achieved. The year can be calculated easily if it is assumed that there are 365 days in the year, and this is the case if all of the leap days are subtracted before this calculation. The day of the year can be found from the Gregorian day from the remainders from this division. Then the month and day can be extracted. The only difficulty is to specify if a day occurs on a leap day. This facility is added to the cumulative leap day calculator by adding a flag called isLeapDay, which will then specify that the date must be February the 29th. All times may now be specified as Unix timecodes. There has been a recent celebration when the timecode read the digits 1, 2, 3, 4, 5, 6, 7, 8, 9, 0 on the 13th of February 2009. The algorithms that I've used may not be the best algorithms for the purpose that I've described, but they appear to work. Only positive numbers work accurately with the procedure prescribed. Extra work would be needed to calculate negative numbers. I intend to continue work on the flashcard program and will use this timestamp to prescribe my future study.